Perfect. Thank you. So, hi and welcome to everyone who's joining us online on YouTube. This is the first cohort of the Effect book. And today we're on chapter 17. So in the methods now, and we'll be talking about event studies. Just as a first thing, I'm just going to skip right to terminology because I was confused when I started reading this because in economics, an event study is a very specific thing within difference and differences.
Yeah.
And this
But
isn't
and by
that.
by the way, I think when we were talking about kind of our familiarity with some of these concepts, early on, I had taken a class in interrupted time series before, but I had not heard of the term event studies. So that was new to me. And it was kind of interesting in the chapter that the author talks about like different fields use different terms, right? So that is not unusual that maybe I wouldn't have heard of event studies. But yeah, I like this chapter. Is it like a nice refresher for me because a lot of it was kind of what I was familiar with, where it's like you're fitting a regression, right? An event happens, maybe there's a policy change or something, new laws passed or something, and you want to see, how that's impacted. And yeah, it's basically a linear model with ARIMA error terms.
Yeah, exactly. So like for me, this is like time series stuff.
Mhm.
So I was surprised when I read this and the stuff I was expecting didn't show up. But yeah, apparently there's even more names for this. So there's interrupted time series, is what you were talking about. And it's also called the statistical process control. And then
Mhm.
the author says there's variance where you control for time with a control group, which is what I'm used to being called an event study. But that's going to be in the next chapter. Yes. So we're basically doing one time series and then something happens and then it changes.
You know,
And yeah.
just going back to that concept, like with interrupted time series, a lot of times you have a control group that you're still looking at. So you fit this model, right, for your cohort of interest. Say there was some sort of policy change. You're testing the coefficients for significance, but then you find a similar cohort, right, that didn't have a policy change, and see if during that same time period, if there was you know, there's some sort of significance to the coefficients post, whenever that interruption or shock event, whatever you want to call it, took place.
Yeah, but that's already difference and differences. So we're really just with
Yeah,
one single thing where
right.
everybody is affected.
Yep.
Yeah, so it's really just the simplest thing you could think of, right? Like you have one observation over time, and then something happens, and then you see if the trend that you had before is still going on. So the author puts it very simply and says whatever changed from before the event to after is the effect of the treatment. And we don't have a control group, nothing like that. And then what I really liked is that he pointed out that many superstitions are very poorly done studies, event studies, so that if you wear a certain t-shirt when your team is winning, then you conclude that it was because of this t-shirt, and now you have to wear this t-shirt every single time because otherwise your team is going to lose. That's a very poorly done event study. And I kind of liked it because I feel like in a lot of settings, you have to think about whether it makes sense what you're doing here, or whether you're just opening up a lot of backdoors.
I found
So
this DAG to be a little bit confusing,
yeah,
even though it's simple. But, time
agreed.
influencing after event, and I think there was some commentary about that, like maybe you don't really need the after event thing as a separate node in the DAG.
Yes. Yeah, but I mean, this is kind of the treatment. Yeah, the after event and the treatment are kind of the same, but you wanted to
Yeah,
pull it apart to have it like more look like the other ones, I guess.
yeah, yeah. So that kind
But
of makes sense, but it's still a little strange to me.
yeah,
I don't know.
yeah. Totally agreed. Like
If
the
I were just
stag
to
looks a bit wonky
draw
too.
this kind of concept, without having a background and what we're talking about, I probably wouldn't have drawn it this way.
No, definitely not. So we're only using within variation here because we only have that one group or that one individual that we're tracking over time. And we're only considering one sort of treatment, and that's when it switches from off to on. So I wasn't wearing the t-shirt before and my team kept on losing. And then that one time I put on my t-shirt and then my team won. That would be the treatment putting on the t-shirt. And no panel data, but instead time series data. And we already talked about the stag. So the obvious backdoor is time going directly to outcome. So that the treatment is happening, but something else is happening as well. So the treatment, let's say with a t-shirt, could be that I put on my t-shirt, but maybe in the same time, my team was getting a different coach. And that probably had more of an effect. So what we need to do is to make sure that this time doesn't directly affect outcome. And we can basically do that by having very short time spans.
And like how you're describing
Time
it, time is kind of like a proxy for other things happening,
Yeah.
right? Like you said, like another coach being hired or something. You could draw that in the diagram, like nothing, new coach.
Yes. Exactly.
But I think the point here is like we don't know all the back doors. We know it's related to time. Therefore, we're just going to simplify and say time is a confounder.
Yeah, exactly. And that also helps us in like thinking about it, because when we say, okay, we're just going to look at a super tiny time window, then time shouldn't have that much of an effect, because like the new coach settling in is also going to take some time, for example,
Yep.
and for the treatment to take effect. So I think that helps us in thinking about how a good event study could work. Okay. So the problem is we always need to have a counterfactual in these cases. And since we don't have a control group in this sort of study, we need to make a counterfactual based on what we see before the event. So for example, in this graph on the left, we can see that there's not really any trend. So it's kind of stationary. And then after the event happens, it spikes and then kind of goes down again. So there's no trend. And then something happens, and like we would just expect this time series to go on in this light gray color, so just to be stationary and not really change. And similar here, we do see a trend that's going upwards, and we would expect something like in the light gray stuff, but then something happens and it changes. So that helps us build up a counterfactual.
Yeah. And I like this example, and I'll just say it like in my actual work, I mean, certainly have done something similar, particularly with COVID. Medical health insurance, it's privatized here in the US for a lot of it is. And you want to figure out how much, COVID maybe changed or dampened, folks going to the provider office. Certainly there were some spikes as well, right, for people getting very sick and requiring hospitalizations. But for things like elective surgeries, those went way down. And so you could essentially just fit a time series, right, prior to COVID and just extrapolate that out to say this is what would happen, had COVID not become a global issue. So yeah, I think that's a like a classic example of an event study, at least in my world, that I've done, right, to measure kind of the cause and effect there.
Sorry. Yeah, definitely. And then you'd probably condition on the age of your total population, because I'm guessing those surgeries are going to become more often once people turn older. Or then, yeah, that makes sense. Let's see. So things that we can do if we have such a trend, and are the first one is we can just ignore the trend. So even if the data looks like that, we could just say, no, we're just going to ignore it. But it's only reasonable if we believe that there's no time effect and if the data looks flat. So like in this figure on the left. And also if we have an extremely tiny time span. So the author was talking about finance, where there's cells in microseconds measured. So if we are talking about like 3 seconds, I think we're good to go with just assuming there's no trend.
Yes, absolutely.
Or maybe even if it's a day, like that's still a very small time span. Then the other thing we can do with a trend is that we can predict the after event data using the before event data. That's basically what we did with this light gray line on the right-hand side, that we said, okay, there was a trend before, so we're just going to continue that trend. And then the third option is kind of like the second option, actually. So we're trying to figure out before the event happened, which variables correlate strongly with the variable that we're interested in. For example, if we're going with the elective surgeries, the percentage of people over 70 in a population. And then we take these variables after the event happens and try to extrapolate from there how the trend would have continued. Okay, we already went through this. So this is already the idea of it. That's all there really is to it. Just going back to this image, so we have a trend or we don't have a trend, and then we just predict from the before event data how this trend is going to continue, and then we compare that to what happens in reality. And then the next 3 chapters that we're going to check out is how this is used in finance as a very specific example, how we can use it with regression, and how we can use it when we're considering time series. So this ARIMA stuff that we talked about earlier.
Yep.
So in finance, this makes a lot of sense to use it because we have a short time window. And because stock prices reflect information about a company. So for example, if we have on the news that there's been that the CEO has died, for example, that is an information about a company, and that's going to be directly reflected in their prices. So there's a lot of events that we can have a look at.
Right. Yeah. The idea being that market's efficient, information should be incorporated almost instantaneously.
Exactly. I think there's a lot of literature on markets not being very efficient. But yeah, that's the basic idea behind it. So what we do is that we have this estimation period before the event, which we use to extrapolate the counterfactual. And then we have an observation period that's basically from just before the event, in case there's any sort of anticipation, I'm guessing, and then to sometime after event. Then we use this estimation period to predict, okay, the predicted stock returns is the variable that we're interested in here. There's a couple of different ways to do this, but because we're both not in finance, I'm not going to go into detail. And then basically you subtract your estimate from what you really see, and then you get the abnormal return.
Yeah, I mean, I think he was just using like what the capital asset pricing model, which is pretty standard. Okay.
And then the author actually gives us an example in code, which I thought was nice. I don't actually know from this. It's from 2015, the data. So we have an estimation period that's 3 months from May through July, and then we have an observation period that's like 3 weeks in August. And sorry for the spamming here.
Yeah, I always do that. You gotta sometimes suppress the messages, right, and markdown.
Yeah.
Forget that half the time myself.
Yes. So we have this Google stock data that's already included with a package that the author gives us. And we filter the data to the estimation data set and the observation data. then we just estimate a very basic model. So we're having a look at the returns that Google has. And since Google is a part of the Standard & Poor 500, we're just modeling as that, like following that general curve. Then we get the abnormal returns by first, so we're taking the returns from Google and then subtracting the mean of what we're estimating should be there. Then the abnormal returns from the market. So the market is just the Standard & Poor 500. And then we're going to predict what should have happened, and then take the difference of what should have of what did happen to what should have happened. Yeah. And then we have a graph. So actually, I'm just gonna pull this in here because here we just see the abnormal risk, the abnormal return risk, but we don't see the other ones. I'm just gonna pull up the plot that he has in the book. Oh, way. Yes. So what we just saw was this risk thing, I believe. And then we can see it's a bit higher than the market. But just after the event happened, it's actually lower than the market. And then the mean is doing something. I don't know. And then you can have a look at this graph and try and compare what you think should have happened is what the market is doing. And then see, okay, so actually my company hasn't spiked as much as the rest. So maybe that was a negative effect for me.
Yeah, I'm sorry. I did read this and I just don't remember. Is the risk part, that's the risk adjusted return? What we would expect based on the market movement?
Yeah, something like that.
Okay.
Honestly, I skipped a bit over it because it's finance.
Yeah. No, that's fine.
But
Yeah,
yeah, I
we don't
think
need
the
to go into
idea
the
is
detailing.
mostly to compare those lines. Yeah. Oh, and that's it. That's how finance people do it. And they probably know more about it than I just said, but that's the basic idea anyway. Then the next approach that he's talking about that I think is a bit closer to home, at least for me, is when we use a regression to estimate or to predict basically what should happen afterwards. So we estimate one regression of the outcome on the time period before the event, estimate the outcome on the time period after the event. So we basically just have a linear regression with a cut in the middle.
Yeah, so we have just basically interaction terms for the coefficient and the slope, right? So it's essentially testing to see whether or not there's, I think that how they describe it in the literature as level changes, which would be like a coefficient change. And then if there's a different trend as well, right, would be the slope change.
Exactly. So I think that's mostly what we're interested in, is whether the slope changes. Because then something apparently happened. And I think that the easiest way to fit this is with a linear model, but obviously it doesn't have to be linear. So you could go with any of the methods that we discussed when we went into the regression chapter. So either use polynomials or just go with the maximum likelihood thing or something like that. In the author's point of view, going with regressions provides a more precise estimate of the time trend than having a look at the plots and two lines and seeing how different they are. But we're limited by shape, as I said. So if we're in a linear regression, it needs to be linear, even if we can extend it with polynomials. However, we are still in the time series world, so we need to really take care of autocorrelation. So using heteroscedasticity adjusted and autocorrelation adjusted standard errors is pretty standard here.
Yeah, I guess it's that sandwich package in R is where they
Mm-hmm.
talk about that. Um, or you could use just bootstrapping to get your standard errors.
Mm-hmm.
And interestingly enough, I'm working on a problem now. It's time series relevant, and I'm using block bootstrapping, which I had not used before, right? So it's just a way to kind of pick up those autocorrelated errors. Um,
Mm-hmm.
so yeah, this book's come in handy.
Yes, it is. So we have a very concrete example. It's about ambulance care. So I think it's in Great Britain, and they trained a couple of teams to become more efficient as a team, and then expected to see an outcome on the heart attack performance. So whether I'm guessing whether people die on the way to the hospital or something like that.
Or some
He
measure of
didn't, re
morbidity, right?
yeah, something bad happening, and the hope is
Yeah.
that by having dream work, teamwork, less bad is happening.
Mhm.
And then he has this um notation of week minus 27. I believe they have 27 weeks before they have this measure, and that's why he put it that way. But I think it looks a bit odd. But the idea is basically that we have this exact same formula as above. So we have um our weeks, then we have a coefficient for after the training, and then we interact that. And this is epsilon. It's cut off a bit.
Yeah,
And
I
then
agree that
yeah,
the centering around 27 is weird. You could have just changed your
yeah,
time scale so that you didn't have to do that.
yes, yeah, I was
But
confused by that.
whatever.
But so the idea is we can fit one slope here before our week 27, and then we can fit another slope here. And I don't know, from looking at it, it could be significantly different, not quite sure. But then he has a table where we actually have a look at the p-values and the confidence intervals, and those two slopes are actually not significantly different from each other. So might have been nice for the team, but it did not help those people with heart attacks.
This is where it's tough, right? Because visually it looks like there is a bit of a change, even though
Mm-hmm.
you don't have statistical significance. So it's
Yes.
one of those where it's like I don't know. In my mind, this is kind of inconclusive.
Yeah, but yeah. I
And
feel
and I think
like also because there's only 27 data points before,
right,
that the slope could be very different based on that. I
that's
mean,
part of the problem, right? Yeah, if they actually that's a really good point. Like if they would have collected more data ahead of time, and it's interesting, you're right, 27 data points before, when didn't they get like a whole year or something like that? Because
yeah.
thereafter is much longer. Um, it's one of the problems when you're dealing with p-values, right? Sample size is so important.
Yes.
Um, and yeah, and I think with interrupted time series like this in general, like generally you're presenting these results to people that are not hardcore into the technical details, and having a diagram of what's happening is pretty powerful for like those people that maybe don't know all the technical details. And
Yeah.
just again looking at it, it seems like there was a change, right? It's visually compelling, even if it's not statistically compelling.
Yeah. But I'm also wondering, we do we allow different y-axis starts for both of those? Or do we make them meet in the same point? Because that's something you see a lot with RTD, right? That things will just jump right at the border.
Mm, yeah,
And then you don't
that's
just change the slope, but you also change
right.
oh, what do you call it in English? Like where the slope starts, basically. I'm not quite sure.
Well,
And we do have the beta 1 and the beta 0, so technically, yes, I
yeah,
guess.
well, mm, mm, mm.
Or the
Yeah,
beta
I'm
2
thinking.
after. I'm very confused.
Uh, yeah, I'm trying to think through that too. Uh,
This is a
Based on how this
dummy.
works, does it have to be does it have to be connected? I don't think it necessarily has to, right? Wouldn't
Mhm.
there could be a jump based on this definition?
Yeah, because we do have the beta 2 after, and that's just a dummy. So there it would be possible to go up.
Yeah, that would potentially create a jump,
Yeah. Okay, but we
a
don't see the jump,
level
so that's
shift, but we
actually
don't but
a
that's
bit of
actually
it.
what you would expect too with if you're not making the change until week 27, you wouldn't necessarily expect things to take off right away. Yeah, there's kind of like folks maybe don't quite get what they're supposed to do right away.
Yeah.
You know, they need a couple weeks to iron out the details. So that's not surprising to me that this diagram shows kind of, a little kink here, but not a level shift.
Yeah. But I think, yeah, it's still like if I prolong this trend, in my eyes, it doesn't go up there. But apparently it does. Anyway. So that's how you do it when you
Yeah.
use a regression. So just basically use an interaction term, then you have two slopes, and that's it. Also not that magical. Um, and then when you take the time series seriously, you basically use ARIMA models. So, oh wait, ARIMA models is only after. Sorry about that. But that will come. So we have some events that impact a lot of different groups. Um, and then it's kind of a question, how do we deal with this? Because before we were just talking about one single group or one single individual, one single stock, whatever. But so if we have a lot of different groups that are all impacted exactly the same way, we could either summarize all of the groups into one, and then we just do it as we did before. But the problem here is that we're losing information and power because we just have less observations. That makes it harder to get stuff significant. We could also treat each group separately and then use separate regressions. So just do what we just did over and over again. But again, then we're kind of losing power. Maybe not the best option. Or you could just aggregate it with a regression and use a group fixed effect for every single one of those groups. I know the group fixed effects are probably gonna come in with difference in different. Oh no, we already had the fixed effects. Yeah, so just instead of a beta 0, we use a beta I, and then we allow the slopes to start at different points, at different intercepts. But we get the mean of the treatment effect. Another problem might be that the event matters differently over time. So maybe let's think about a vacation that people take, and the week or the day right after, people are still super relaxed, very focused, but then maybe 2 weeks after the vacation, the event doesn't really matter anymore because you were stressed out again. So what the author suggests is to leave out the time just before the event kicks in to make this a bit easier, to use standard errors adjusted for each period, and make everything relative to the period before the event. So then this would be the regression, because you have so you have the different times beta t. So kind of a simulation, I guess, because we're just creating this data set. So yeah, as in the simulation chapters, creating a data set, and then we just run a regression with different dummies basically for every point of time. And then we also cluster them based on the ID. And then we see this graph that kind of looks familiar, I think, for event studies also later on, and see that, okay, just in point of time 6, we apparently do have a significant effect. That's because we put it in here.
Yeah,
And that's
yeah.
lovely.
Mm-hmm.
But we also have we don't have a significant effect.
I thought we had some other ones in here too. Yeah, unexpected,
Yeah.
significant at 2 and 4.
Yes. Maybe I copied out the wrong one because in the book it definitely looked like it. Okay. How did that change? I'm confused. So anyway, the one at 2 is also significant, but negative, but it shouldn't be based on our data generating process. And then
Right,
7 and 9.
right, because those are the confidence intervals, right? And
Yeah,
2 here is, yeah, looking significant, but it shouldn't be because we know the data generating process.
exactly. And I mean, if we think about pre-trains later on, this would kind of kill the whole thing. Yes, but we also have a super small sample size.
Yeah,
So that's kind of what explains this.
yeah, and I'm guessing. So is that the actual? Did you make that chart? Or did you copy that one?
No, oh wait, I think this is what I made actually, yes, but just
Okay,
copying his code.
right. It was a different seed, right? Or you probably
Yeah.
ran it multiple times or something like that. So it's just you're gonna get a different result. Yeah,
Exactly.
that makes
So this
sense.
time it actually worked out exactly the way we wanted to, but
Yes.
it won't always. And now we finally get to the ARIMA models. So we can also do the whole event study when taking into account time series forecasting. And that is a whole different world of itself. So the author points us to other books if we really want to go in depth. But
Yeah.
basically, we're taking care of autoregression, which is that the value is going to depend on the last value. And we're taking care of the moving average, which is that the standard errors are correlated, basically.
Errors are
And then
correlated
we
over time.
can,
Yep.
hmm?
Yeah, I'm just agreeing with you.
Yeah, cool. So, and then you can do this for however many lags you want to. Here we just see an AR1 model where we have y in time t, and that's correlated with y in the time before. And we have an MA model of 1, and there the error term, yeah, we add to it something from the error term from the time just beforehand. And then you can mix and match that. So if you want to have an ARMA process of 2, 1, so 2 for the AR and 1 for MA, then you get 2 lags for your value and 1 lag for your error term.
Yeah,
And
and I think in most
yeah,
cases you want to account for this, assuming you have a lengthy enough series that you could actually capture these effects, because otherwise your standard errors are probably going to be too small, or right? And so you'd be capturing significance when there really shouldn't be. I think that's
yeah,
the important part here.
definitely.
And I know when
So
I took
yeah,
this interrupted time series course, there's like I think it's in the NMLE package. There's a GLS function, generalized least squares, that allows you to just specify the order of the autoregressive or the moving average
yeah,
terms.
there's a lot out there
There's
to
a
like
lot.
try to find the right specification, right? Then there's
Yeah. And there's
yeah.
auto ARIMA type stuff going on there too, so you don't have to actually
Mm-hmm.
do that much experimenting, and that usually does a pretty decent trick at it too. I've been using I don't know if you've used this, the Fable package in R, which is really nice interface for doing anything
Mm-hmm.
time series related.
Yeah, I think he actually also recommends that. Yeah.
Oh, there it goes. Yeah, that's a good one.
Yeah. Um, so just thinking about what do these processes do? If it's totally random, we just see this random walk centered around 0. If we have a moving average, we can see that the spikes are kind of correlated. So if there's really big spikes, then larger spikes are going to follow in either direction. There's smaller spikes, that they're going to be followed by smaller spikes. Then we can see kind of that we have many trends in here, I guess. So like the past value is a good predictor of the current value. And then if we put those two things together, the process becomes a lot smoother, actually. It's not as noisy anymore. Yeah, which is
Yeah.
something to
I,
take
I will
care
say
of.
just looking at these, it's hard for me to distinguish like, oh yeah, of course.
Yeah,
The one in the upper right is a moving average lag one process. Like that doesn't really,
agreed.
it's hard for me to internalize that. I don't know if we're supposed to, but I'd
I
have
hope
to
not.
I'd have to play with the models. I couldn't visually identify it here. I mean, I think, you can use those like autocorrelation plots and partial autocorrelation functions to kind of, if it's a pure autoregressive or moving average, like there
Mhm.
are some visual indications, but just looking at the raw time series, it's tough
Yeah.
uh, to really
I mean,
figure out
that's
what's going on
also
there.
what all of those tests are for, to figure it out. Because I
Yeah,
think, yeah, as I agree, visually it's difficult. I mean, sometimes you do see these time series where it's like where it's not fluctuating as much, and then suddenly it's fluctuating a lot, and then again not at all. And I think that would
yeah,
be an easier one for a moving average, but otherwise, yeah, hard.
it's tough.
Okay. It's already the last slide.
Yeah.
So the event study basically combines the event study effect. So like the effect that our event should have and the model that we are using to create our counterfactual. So if we're testing something, we actually test both at the same time because we can't disentangle them, right? Because we have the data that we're measuring with the actual effect, and then we have our model, and then we take the difference. So there's no way to disentangle that when we have this effect going on. So one way to deal with this is to use placebo tests where we know that there shouldn't be an effect. And
Hmm.
then if we do find something after all, then it must be because the counterfactual model is wrong and
Yeah.
it's not working.
I thought this was a really, really cool idea. Didn't think about this. I think just in so much real world work, you just kind of assume the model is correct. In this case, your counterfactual model. Just take that as a given. But of course, a lot of times your model is not quite right. And yeah, I thought this was a neat way to go about troubleshooting it.
Yeah. I don't know, like, so in my field, there's actually a lot of placebo stuff going on,
Hmm.
especially in what we call event studies, so like difference and differences. So you just try
Yeah.
to take a year before and see if anything happens, or if it's supposed to happen in wintertime, you take something in summertime, and then you try to convince people that because you can't see anything there, this should hold up. But then again,
Yeah.
I'm always wondering if people aren't cherry picking the placebos that don't work
Oh
and
yeah.
just don't report on the placebos where you do get something. I
You
don't
know
know.
that some people do that. It's unfortunate, but true.
Yeah. All right, that's all I got. If you don't mind, we can just finish up early
Yeah.
today.
Yeah, let's do that. I'll hit end.